Okay, so here is video review for topic 5, algebraic models. This one will be on the math models reassessment, if that's one that you are realizing you should probably do. This is going to be the math models one. Okay, so in this video we're going to cover exponent rules, solving exponential equations, and making an exponential equation for a word problem. Alright, so here first are the exponent rules, just to recap. When multiplying powers with the same base, keep the base and add the exponents. I'll jot down just what that looks like. So x to the a multiplied by x to the b. Multiplying powers with the same base, keep the base, so still x, and add together the two exponents, a plus b. When dividing powers with the same base, keep the base and subtract the exponents. So that would be x to the a divided by x to the b, and the answer to that will look like x to the a subtract b as a new exponent. When raising a power to a power, keep the base and multiply the exponents. So here's a power raised to another power, like stacked exponents, and this one will come out to x to the a times b. So keep the base the same and multiply the exponents. In order to simplify an exponent or a power, you can use all of these exponent rules or power rules and keep as a power. So if the instruction says simplify, you're going to keep as a power. To evaluate negative exponents, we have another exponent rule. We can flip the base and change the exponent to a positive. So if the exponent happens to be a negative number, flipping the base means take a reciprocal and change the exponent from a negative to a positive. And this means the same as 1 over x to the positive a. Because 1 multiplied by itself as many times as you want is still 1. So the numerator simplifies nicely in this one. The last exponent rule is changing between exponential and radical forms. Radical is a root. And with this one, I think I mentioned flower power as a visual way of remembering this one. And these are questions where the exponent is a power. The denominator or the bottom of the power is like the root. So we're going to take a root. And the numerator of the exponent is the power, so that's like the flower power part. So it stays a power. So the bottom is the root, the numerator is the power. And this one actually can be written in two different ways. We're going to take the nth root, but the exponent can happen after the root, or it can happen inside the root. It can happen in either place, and we'll get the same answer. So there are our exponent rules, and we're going to apply those in the next section here. So the instruction says simplify, then evaluate. So this is important to pay attention. Simplify means we're going to leave our answer as a power first, a simplified power, and then find a final answer. So you will not earn full marks ever for just saying the final answer, like the final number answer. That's not going to do the trick here. We need to do the simplifying using exponent rules. So there's a few things going on in the first one. There's two powers being multiplied. The answer to that is being raised to another power, and there's also a division. So there's a bunch of rules we're going to be able to use. To start, I'm looking inside the bracket and seeing two powers multiplied together. So I'm going to keep the base for those powers and add the two exponents, 2 plus 3, to get 5. Everything else about this question is going to stay the same so far, so I'm only going to make that one change in my first step. Next up, I'm looking at this numerator. There's still a bracket here, and I want to get rid of it. So I'm going to take my power and raise it to another power. That's using the power rule, where we keep the base and multiply the two exponents together. 5 times 2 is 10. So there's a little bit left to do here. There's still a division that we're going to need to carry out. And the division rule, or quotient rule, says keep the base the same and subtract the exponents. 10 take away 6 is 4. And for this part, you can grab a calculator to do the last piece of this for us when we evaluate and get a final answer, and it's going to be 256. Okay, so exponent rules, and then finally a calculator step. All right, the next one looks a little bit ugly, but it's actually a nice short solution. There's a power raised to another power, and the power rule is nice and simple. It says keep the base and multiply the exponents together. 1/2 times 4. 1/2 times 4, or 1/2 of 4, is 2. So with that simplification, I've got nothing ugly left. This is ready for a calculator. 36 squared is 1,296. Okay, so there is, sorry about that. There is another option for this one. I could have noticed that there was a fraction exponent and chose to deal with that part first. I could have rewritten that as the square root of 36, which is 6. And that would have led me to doing 6 inside the bracket, raised to the power 4. And that is the same answer. So a totally different approach that would work just as well. Maybe I'll jot that down here. The square root of 36 squared. Square root of 36 is 6 squared. Oh, there's a 4 on the outside there. My bad. That outer exponent was a 4. Fix it here as well. And 6 to the exponent 4 is also 1,296. So you can pick either approach. You can do the power rule or change to radical form and get the same final answer. All right, next up is 2 powers of a base of 16 being multiplied, and this time it looks gross because the exponents are fractions. Okay, so we could jump right to a radical form, or deal with the multiplication rule first, the product rule, where we keep the base the same and add the two exponents. That sounds like an easier start to me, so I'm going to go that route. So I'm going to add together the two exponents. Luckily, they have a common denominator, so they're going to be nice and easy to add. Negative a quarter plus 3/4, or if you think of it in the other order, 3/4 take away 1/4. That'll be 2/4, or we can reduce that to 1/2. So a little bit of like side thinking there. So I've used the multiplication rule, added the exponents together. I'm noticing they're fractions, so I have to be careful with my fraction addition. I get 2/4 and then reduce it to 1/2. All of those steps have gotten me to the point where I have a power, just one single power. I can either grab my calculator at this point or probably do one more step. The fraction exponent is a clue to me that I can use radical form. And the square root of 16, I actually know that. I don't even need a calculator. So that one's done. All right, our last one of this type with just exponent rules is similar to the last one, but instead of a multiplication, there's a division. So my first step is going to be using that division or quotient rule, where I keep the base the same and subtract the exponents. 8/3 take away 2/3. I'm being careful to write my exponents raised and small, so they look like exponents and they don't kind of blend in with the 7 base. So in my exponent, 8/3 take away 2/3, that is 6/3. 6/3 is equal to 2. So with all of it simplifying, again, I don't really need a calculator. I know that 7 squared is 49. And so all of this stuff is simplifying, making the powers look nicer. And this last step is the evaluate step. Okay, so with that original instruction, simplify then evaluate, I do expect that there is process shown, the exponent rule being shown. All right, next up, change to radical form and then evaluate. So this is similar to an exponent rule question. Changing to radical form, this is the one with the fraction in the exponent. So for this, we're going to keep the base. The big number is 81. There's going to be a radical, and the denominator of the radical is the root. So I'm taking the fourth root, and the numerator of the exponent is the power. So I'm going to be raising to an exponent of 5 at the end. So that is now in radical form. You can grab a calculator to do this, possibly. There's going to be a button that looks different on everybody's calculator. On mine, it sits above my exponent button. So I have a hard button, or like a pushable button that says YX, Y to the X, and above it there is X root. So this is a pick your own exponent, and this is a pick your own radical. So I'd have to use my second function and then click that button to use it on my calculator. If you need help finding that on your own calculator, you can ask me during drop-in help. Anyway, the fourth root of 81, the number that you can multiply by itself 4 times to get 81 is 3. So the fourth root of 81 is 3, and we're going to raise that to the exponent 5. And then 3 to the exponent 5 is 243. Okay, so I know evaluating the radical might be tricky on some of your calculators, so please ask for help if that's not working well for you. All right, next up, the instruction says evaluate. So you don't have to show simplifying, you just need a final answer for these ones. There's a couple of interesting things going on with these exponents. 2 of them are zeros, and 1 of them is a negative exponent. And we haven't practiced those yet today. So anything raised to the exponent 0, let's do a little recall. Anything raised to the exponent 0 has an answer of 1, no matter how weird that base is. It could be a whole number, a fraction, a decimal, but if it's raised to the exponent 0, the answer is 1. That means this answer is 1. The next one feels a little bit too easy after that. And I want to just point out that the exponent 0 is attached to the 16. There's no brackets here, so it's not, this is different than negative 16 to the 0. They're not the same. Having brackets around your negative changes this question, and this one does not have brackets. So this one has a negative sitting out front, and then 16 to the 0, which is 1. So this has an answer of negative 1. This other question that I've added here is a bracket raised to the exponent 0. That has an answer of 1, positive 1. So careful with the negatives. Pay attention to whether it's included in brackets or not. The exponent only applies to the thing it's directly touching, in this case the number 16. And this earlier one, it was touching the bracket, so it applied to everything in the bracket. So just pay attention to that. The last one of this type has the negative exponent. The exponent rule, just to remind you, says we can flip the base and change the exponent to a positive. So here I changed from an x to 1 over x, and the sign of the exponent has changed. What that looks like here is a flipped base. Instead of 2 over 3, I'm going to change it to 3 over 2. And the exponent changes from negative 4 to positive 4 when that happens. So now this is a fraction raised to the exponent 4. That means 3 to the 4 divided by 2 to the 4. And you can grab a calculator for that, or maybe remember that 3 to the 4 was 81, and 3 to the exponent 4 is 16. That can't be reduced at all, so that's the final answer. I'm not going to grab my calculator to change it to a decimal because it's just the same answer in a different form. Alrighty. Well, last two questions with these algebraic models. Number 4 says solve by first writing with a common base. Solve by first writing with a common base. So it's like a change of base strategy. What that means is that on the left side of the equation, I want to see a power with a base. And on the right side of the equation, I want to see a power with the same base. What I'm going to be doing here is rewriting the number on the right side as a power of 4. So this is maybe going to be helpful with a power chart. I shared one of those with you before. If you're not comfortable, if you haven't got them memorized, but 4 squared is 16. So I know that one as a fact, but you can play around with that. You can try with your calculator 4 squared, 4 cubed, 4 to the 5, until you see an answer of 16. So you can try typing in different exponents until you get the right answer, and use a guess and check strategy there, or the power chart that I shared in D2L. At this point, the bases are the same. Bases are the same. My little acronym for that was BAT. Bases are the same. So we can ignore the bases and focus on the exponents that must also be equal. And this question's done. So it's been solved without doing too much fancy stuff there. The next one has a little bit of rearranging that has to happen first, because there's 3 terms, and I need to have only one on the left, one on the right for this strategy to work. So I'm going to move the 4 to the other side using addition. I'm going to add 4 to both sides. Now I've got a power on the left, a number on the right, and I'm going to rewrite 32 as a power of 2. And that one is 2 to the 5. Once the bases are the same, I can focus on the exponents and say that x must be equal to 5. So the last one, there are powers on both sides of the equation. On the left, the base is 3, and on the right, the base is 9. 9 is a bigger number, so I'm going to adjust that one to give it a smaller base. So 9 is equal to 3 squared. So 9 is 3 squared, and there's still an exponent of x plus 1 that needs to be applied. So this needs a little bit of exponent rule simplifying to tidy up the right-hand side. A power raised to another power, our strategy was multiplying the 2 powers together. And here that's going to need us to use distribution. We're going to multiply both of those things by 2. So 3 to the x equals 3 to the 2x plus 2. And now the bases are the same. I can start working on my exponents, which also must be equal. X from the left is equal to 2x plus 2 on the right. I've got a little algebra equation that needs to be rearranged and solved here. Let's see. I'm going to subtract x from both sides and subtract 2 from both sides. If I take away x from both sides, I'm left with an x on the right. And if I take away 2 from both sides, I'm left with a negative 2 on that side. So that's finished. All of these solving equation questions could be checked. by substituting your answer for x. Check using substitution. So I've discovered that x is 2. If I put a 2 into this exponent, 4 squared, hey, that is 16. That worked. So you can do a little self-check that way. Okay, the last one here is from a word problem. It says an initial colony of 1,000 bacteria grows at a rate of 25% a day. Determine an equation and find out how many bacteria there will be in 10 days. Okay, so determine an equation. This is exponential growth because it's growing not by like doubling each day, or not by adding 2 each day, I mean, but by a multiplier, 25%. So the exponential general formula looks like a multiplier in front of a power. So some base raised to an exponent, and the multiplier in the front is like your initial value. Initial value or starting value is what the A is. I just want that to pop a little bit more. Okay, so in this question, we're told the initial colony is 1,000 bacteria, and this other piece has to do with the growth. That's what we're doing with the power in this question, multiplying by some base again and again and again every day, and that's going to grow the bacteria population. I'm going to add one more kind of version of that formula that we saw in our lessons, and it was where we took the base and realized that if it was growing, if our population was growing, that must mean that our base is something bigger than 1. So we're multiplying by a number higher than 1, and that's going to grow the population. We saw a few other questions where there was decay, exponential decay, like the depreciation in the value of anything really. And in that case, you would have 1 as your starting number, and you would take away the decay rate. So it could be plus or minus. R is the growth or decay rate. So R is for rate. So in this question, I'll get my pen set up again. In this question, the initial value is 1,000, so that's what goes out front. In brackets, I'm going to have 1 plus my growth rate. It's shown in percent form, but to add it to 1, I need to change that to decimal form. So dividing by 100, we'll put that in decimal form. I can simplify that one last time. Inside the bracket, I have 1.25, and then raised to the exponent x. So there's my ready to go equation. So there's the equation. And then we're going to figure out how many bacteria there's going to be in 10 days. So we'll use the equation. In 10 days, x is going to be 10. And I'm going to use the equation to solve for y. So starting with a population of 1,000, and we're multiplying by 1.25 10 times. And the power is the quickest way to do that. So on my calculator, I'm going to deal with the exponent first. 1.25 raised to the exponent 10. And I'm seeing an answer of 9.313. 9.3132257. So it goes on and on and on and on and on. I probably don't need all those decimal places, but I need to multiply that answer by 1,000. I'm still leaving that 9.3 number on my calculator, and then just going to hit times 1,000 equals, and I see 9,313. I'm going to round it off. We're talking about a number of bacteria, so I don't want a fraction of a bacteria. I'm going to round off to the nearest whole number. Alrighty, so there is a word problem involving exponential growth in this case. I'm just going to get rid of that little negative down here. But if there was a decay question, the only change that would be made is we would do 1 minus r. Has a negative here. Alrighty, so that's it for our algebra models.